Hello friends, very good afternoon. Myself Dr. M.H. Annaya, and in today's video we are going to work out a problem on an open ring of circular cross section which can be considered as a curved beam. Friends, the question for today's video reads like this: an open ring of circular cross section is subjected to a load is P, that is given to be 25 kilonewton. This P is 25 kilonewton, and this cross section is circular, and we have been asked to find out what are the stresses due to this load at the extreme fibers, that is at A and at B. A is the outer fiber, B is the inner fiber, and this C stands for the center of curvature. Then the second part is what is the maximum stress, whether it occurs at A or at B. Then what is the maximum shear stress and what is the location. So all these things being asked. Friends, if you just take out this figure, the circular ring, when this is being pulled by this pull P 25 kilonewton, it's very obvious that the inside member, that is inside fiber at B, undergoes tensile force, and at the outer fiber A, it undergoes compression. It's very obvious from the diagram itself. And so friends, I will tell you a very simple procedure how to go ahead with this. Friends, in the machine design data handbook, if you refer to, there are equations which will give you the value of stress at B and at A. And I have shown here the cross section is subjected to a tensile load. So across this cross section AB, which is called critical cross section, that is the cross section which undergoes maximum stress, is given by this formula. We can say, to start with, stress at B, stress at B, the inner fiber, the total stress is given by the formula. I can call it as sigma I, stress at the inner fiber, that is at B, it is at B. Inner fiber is B, outer fiber. Is given by the formula sigma direct plus sigma bending at the inside fiber, sigma D plus sigma Bi. And friends, this sigma D is the direct load. In this case, this load P causes at this critical section a stress equal to P divided by area of cross section. So I will say P divided by A. P is the load, capital A is the area of cross section, plus sigma Bi, that is the bending stress at the inner fiber, is given by the formula MB into Ci divided by AERI. This is the formula which is available in machine design data handbook in this chapter, curved beams. Friends, what are these values? You just write down. P is the load. There is a tensile load here, that is 25 kilonewton, 25 into 10 to the power of 3 Newton. And capital A stands for the area of cross section, that is given by pi by 4 into d square, that is pi by 4 into diameter of this is 100 square. So you can get the value. Then comes friends MB. MB is the bending moment due to this eccentricity is given by P into RC. So P is 25 into 10 to the power of 3 and RC you will have to find out. So friends, in the second step, after getting this information, we will find out what are these values of RC, etc. Friends, please remember in this chapter, the second step, what I am going to tell you is very, very important because the cross section of this curved beam could be trapezoidal, which is very common, or I section, or T section, or rectangular section, along with this circular cross section. And we have got formulae in the machine design data handbook given in the form of a tabular column, wherein you can get all the information about the cross section. Friends, I will say here in step number two, you will find out what is RC, or you can say to find RC, RN, then CI, comma C naught. I will tell you what are these. E, then comma RA, comma R naught. So these are the 7 parameters have to be calculated very accurately up to 4 decimal places of accuracy. So find what is RC. So to explain these terms, I am going to write down a very big cross section. That is, I am going to enlarge this cross section and tell you what are these various terms. So I will mark here C. This is here. This is our point A, the outer fiber. This is the point B, the inner fiber. And friends, here the distance from center of curvature to the inside fiber B is called Ri. So write down here Ri. This is Ri, friends. And from the same center of curvature C till that last line is called R naught. This is R naught. You know, friends, for this circular cross section, the center of gravity is here. So we will call this as O, center of gravity, and the distance from here to here is called RC. RC is the distance from center of curvature to the center of gravity, CG of the cross section. It could be a rectangle, it could be a square or a trapezium, whatever it may be. You have to find out that. Friends, then there is a line or an axis called neutral axis, which I call it as Rn. Rn is the neutral axis which is little interior, little lesser than this RC. And the gap between this RC and Rn is called E. E is called the eccentricity. Friends, then from this Rn to the inner fiber, this point B is called Ci. Ci. And the distance from there till last is called C naught. I will explain very clearly all these parameters. So Ci and C naught, horizontal line. This is C naught. So friends, let us find out what are these terms and what are the values of these terms. Friends, Ri was given the diagram, it was 60. Ri is 60. That is from the center of curvature till here I had marked as R. RA is 60. R naught. Please see the diagram, understand clearly. This is 60, this is 100. So 160 is the value of R naught. 160. Then friends, RC is the distance from the O, the center of cross section, to C. So this is RI plus B by 2. RI plus B by 2. RI is 60. B by 2 is 100 by 2. So it works out to 110. 60 plus 50. All in millimeter. Then friends, we will find out the other parameters. Next is, we have to find out what is Rn. Rn stands for the distance of the neutral axis, that is this axis, from the center of curvature C. Friends, for circular cross section, if you refer to the data handbook, we have this Rn is given by square root of Ri plus square root of R naught whole square by 4 is a formula available in machine design handbook. Root Ri plus root R naught divided by 4. Friends, Ri is 60, R naught is 160 and this is by 4. If you simplify, you get this as 103.99. 103.99 millimeter, because these are all the distances. So Rn we have found out. We know Ri, the distance from center of curvature to the inner fiber B. R naught, the distance from C to this. Ri plus D, we have got the value already, 110, 160. Rc is 60 plus 50, 110. Rn we have calculated as 103. Friends, once you know this Rn, we know Rc. The gap between Rc and Rn is called E. E is equal to Rc minus Rn. So 103.99 minus Rn value, that is Rc, sorry, not, it is 110. 110 minus 60 plus 50. 110 minus 103.99. Friend, this works out to 6.01 mm. Friends, we have got all the values excepting Ci and C0. If you see the diagram, friends, this Ci, distance from the neutral axis to the inner fiber, is Ci, which is nothing but Rn minus Ri. From Rn, if you subtract Ri, you get Ci. So Ci is equal to Rn minus Ri. Ci is equal to Rn minus Ri. Rn is equal to 103.99 minus Ri is 60. So this will be 43.99 is the value of Ci. Then C0, friends. C0 is what? From this neutral axis to the outer fiber. That is nothing but R0 minus this. Or you can say this total is D. If you subtract Ci, you will get this value. This is D minus Ci. Small d minus Ci. Small d is 100. Ci is 43.99. So this will be 56.01 millimeter. Friends, the second step is a crucial step and you have to calculate all these very accurately. Then only you will get the correct solution for these. Friends, now we will move back to the second step, that is, therefore this MB what we want is P into RC. P value is 25 into 10 to the power of 3 Newton. RC is Ri plus B by 2. that is 110. So you will get the answer MB. So friends, we will substitute all these values in the formula and find out what is sigma I stress at B. B is the inner fiber, that is sigma D plus sigma Bi. So this is sigma D. P by A, P is 25 into 10 to the power of 3 divided by area of cross section is pi by 4 diameter square. Diameter is 100 for the cross section given. Plus sigma Bi MBCI. MB is 25 into 10 to the power of 3 into 110. This is MB. CI value you have calculated already. That CI is 43.99 divided by AERI. A pi by 4D square. Eccentricity 6.01 multiplied by Ri, which is 60. So friends, we have made the substitution of all the values, and friends, this works out to sigma 45.897 45.897 Newton per mm square. So, because of this load P at the inner fiber, you are going to have a stress equal to 45.897 Newton per mm square. Friends, on the same line, we will find out what is the stress at the outer fiber. The outer fiber is, if you refer to the figure, it is A. I will say sigma O at B. Sorry, at A. A is the outer fiber. Is given by the same formula P by A plus sigma B naught is a formula, and this is written as P by A. This is B minus MB C naught. Formula is available in the handbook, divided by AE R naught. So friends, in this value, if sigma Bi is positive as this case, sigma B naught will be negative. So that's why minus sign here. If sigma Bi is positive, sigma B naught negative. If sigma B naught is negative, sigma Bi is positive. That way. So this will be, friends, P by A minus MB C naught divided by AE R naught. Friends, P by A, P is 25 10 power 3 load, area 5 by 4 diameter square, that is 100 square, plus MB 25, sorry, this is negative here, 25 into 10 to the power of 3 into 110 is MB. C naught value is 56.01 divided by the value of this A 5 by 4 100 square diameter. E is 6.01 we have calculated. R naught is 60 plus 160 D plus RA. So friends, if you simplify this, you will get sigma O at the outer fiber as minus 17.21 minus 70.21. This is the total stress of the outer fiber. So friends, we have found out the stress at the extreme fibers A and B, maximum stress and its nature. Friends, if you see the stresses at the inner and outer fiber, at the inner fiber, sigma I at A, we have calculated as 48.897, 48.45.45 0.897 Newton per mm square. Sigma O is at B. At the inner fiber is B, outer fiber is A. Outer fiber O, inner fiber I. This is the value. And we can very easily say that the maximum stress or the resultant stress occurs at B, the inner fiber of the circular ring. So its magnitude is 45.897 Newton per mm square. And at the outer fiber A, you have the stress minus 17.21 Newton per mm square. So this is the maximum stress. And at this point, I would like to inform you, for all the crane hook, which is also a curved beam, generally made of a trapezoidal section. Whether it's a trapezoidal section, I section, T section, rectangular or circular, these are the only cross section how this is made. So the inner fiber is subjected to the maximum stress always. And this is the answer for the second part. Then he is asking you maximum shear stress. Friends, the stress at the inner fiber is tensile and its value is 45.897. And maximum shear stress. Friends, the maximum shear stress occurs where maximum tensile stress occurs. In this case, maximum tensile stress occurs at the inner fiber B, and maximum shear stress also occurs at B, the inner fiber, and its magnitude, its value will be equal to sigma tensile by 2. Sigma tensile is sigma I at B divided by 2. And this works out to 22.45 Newton per mm square. So friends, we have got all these values. Its location I told you is at the inner fiber. And plot the variation of stress across the critical cross section. Friends, this is also one of the important steps which all engineers should know. So friends, we have been asked to draw how these stress vary across the critical section. Friends, for this, I am going to write two vertical lines, parallel lines, and this is nothing but the diameter. If it is rectangular section, it is going to be B, the critical cross section, that is circular cross section. And friends, here I am going to plot the value of the direct stress, the value of the bending stress, then the resultant stress. So here I am going to plot sigma direct, here I am going to plot sigma B, and finally I am going to plot the resultant stress sigma R. So sigma R, I can say sigma I here and sigma O here. This is our point A, this is B, the inner fiber, the outer fiber, outer, inner, like I am going to mark all these points. So please follow clearly. It is a very simple step. Already you have made the calculation for all the stresses, direct stress, bending stress, and then the shear stress. Friends, sigma direct is given by the formula P by A. So generally for all the problems on this chapter, load should be given. Area of cross section will also be known based on the cross section. It could be trapezoidal, circular, etc. So friends, We have calculated, we know the load, we know the area, we have calculated. So I am going to show the magnitude of this load. In this case, this is tensile in nature throughout the cross section. In the same problem, if the load instead of acting upward, if it were acting downward, then this would have been compressive. So we will take up problems later on based on such concepts. So friends, here this height will give you the value of sigma d. It is constant throughout the critical section AB of the curved beam. Then here I am going to mark a line to indicate the neutral axis Rn. Rn also I am going, neutral axis I have plotted. And friends, here on this line I am going to plot the bending stress. So here it is going to be sigma bi, or I will set it a little closer. This is sigma bi at B and sigma b naught at A. The value is sigma b naught. Friends, we got the value of sigma ba, that is MBCI by AERI. We got a positive value. So I will show this as the value of sigma bi. It's a positive value. It's a positive value. This is also positive above the reference pole. So here we got minus 11 point something. So I am going to join these two by a curve. And here this portion is subjected to compression because this is sigma BO is compressive. We have done already. And this friends with tensile. So it's only a convention for marking these values. So this is sigma b naught, which is negative. Sigma bi is positive. What is sigma I here, friends? You know, it is a sum of sigma direct plus sigma bi. Sigma direct plus sigma bi. Friends, you know here, this is positive and this is positive. So at this point B, the maximum stress, sigma I, positive plus positive. I have to just add these two heights and get a value. So this value is going to be sigma direct plus sigma bi. That is a positive quantity which is called as sigma I at the inner fiber. Friends, at the outer fiber A, this is positive and this is negative. So you are going to have a value difference of these two somewhere here, say. And we are going to join these two by a curve. Friends, it's very easy to understand. And here this sigma O, whatever you are writing here, is sigma O at A, which is equal to sigma D minus sigma Bi. There it is plus sigma Bi and this is sigma B naught. Stress at the outer fiber. Friends, this height is the difference between these two. This height is the sum of these two because both are positive. I have just summed up those two. Here one is positive, other is negative. The result is negative. So friends, this is how the stress varies at the critical cross section of any curved beam. And here is the case of a circular beam with open ends subjected to tensile load of 25 kilonewton. Friends, I hope you are convinced with the presentation I have made. Friend, if you are able to follow this clearly, then you can work out any number of problems on this chapter. The concept is the same. whether you have a circular section like what we had, or a trapezoidal section, which is a very common case in case of these curved beams. And friends, please go through the complete video. And if you like this video, please share this with all your friends. Have a wonderful day. I thank you very much for watching my YouTube video.